Everywhere we look, clocks are ticking, on wrists, on walls, in satellites orbiting above our heads. Their hands move forward with patient rhythm, measuring our lives into seconds, minutes, and hours. We build our world upon those steady beats. We schedule, we plan, we grow old by them, and through it all, we assume time flows evenly, as though the entire universe shares the same pulse. But it does not. The universe disagrees. High above Earth, satellites drift in their orbits, carrying atomic clocks that count vibrations of cesium atoms with astonishing precision. Down here on the ground, our clocks beat in sync with them, only because engineers labor endlessly to correct the difference. The satellites' clocks run faster. Gravity is weaker up there, and that weakness gives time a little more room to breathe. Without those corrections, the navigation systems we depend on would falter within minutes. Our phones would not know where we stand. Our world of precision would collapse into confusion. The reason for this discrepancy lies not in engineering, but in the nature of reality itself. For centuries, we believed time was absolute. To Isaac Newton, time was a grand metronome, ticking uniformly for everyone, everywhere. It was a stage on which the universe performed, but never a participant in the play. Events happened within time, but time itself remained untouched. Yet that comforting certainty began to crumble at the dawn of the 20th century, when a young patent clerk in Switzerland dared to ask what no one else had. What if time is not the same for everyone? What if the flow of seconds depends on where you stand, how you move, and how deep you sit in gravity's embrace? Albert Einstein's insight shattered the illusion of universal time. His theory of relativity revealed that clocks in motion tick differently than those at rest, and that gravity itself bends the rhythm of passing moments. Time is not a river flowing at a steady rate. It stretches and squeezes, bends and curves. It responds to the presence of mass and motion. It is not universal at all, but local, personal, and dynamic. Imagine two astronauts drifting side by side in the void. One hovers near Earth's surface, where gravity tugs strongly. The other floats farther away, where that pull weakens. Each carries a perfect atomic clock. To them, the seconds seem identical. But if they reunite later and compare their clocks, they will find disagreement. The astronaut closer to Earth has aged ever so slightly less. Gravity has slowed their time. What feels identical in experience diverges in measurement, revealing that time itself has been reshaped by the geometry of space-time. This revelation changes everything. Gravity is not merely a force pulling masses together. It is the bending of the stage on which time and space unfold. Where gravity grows stronger, time slows down. Where it weakens, time accelerates. Every massive body, a planet, a star, a black hole, reshapes the rhythm of the universe around it. Your heartbeat, your breath, the flicker of a distant quasar, all pulse at different rates, woven into a cosmic fabric that never flows evenly. On Earth, this difference is almost invisible. A mountain climber experiences time flowing faster than someone at sea level, but the difference is tiny, mere billionths of a second each year. Yet this subtle effect proves that even our most familiar surroundings are warped by gravity. We live inside a distorted continuum, feeling normal only because we share the same distortion. Our minds are tuned to our local flow, unaware that the cosmos beyond ticks to another beat entirely. Every orbiting clock tells a story of how space and time entwine. In the emptiness between planets, time loosens its grip. Near massive bodies, it tightens. The universe, seen through the lens of relativity, is not a static grid, but a living fabric, stretching and contracting under the weight of stars and worlds. This is why Einstein replaced Newton's rigid frame with something more profound: spacetime, a four-dimensional tapestry where motion through space affects the passage of time, and gravity itself is geometry made visible. We are passengers within that geometry. Every movement we make, every orbit and rotation, is guided by the curvature of space-time. We do not feel the bending directly, but its fingerprints surround us. Light from distant galaxies arrives stretched and redshifted, its waves elongated by expanding space. The path of every planet curves not because of an invisible force, but because space itself is curved. And within that curve, time flows at a pace set by the depth of the gravitational field. Where curvature deepens, moments linger longer. Our daily intuition cannot easily grasp this. We are used to linear time, clocks marching steadily forward, causes preceding effects. Yet nature whispers a different story. The ticking of a clock depends on its journey through space-time. It depends on how fast it moves and how close it resides to the sources of gravity. Even light, the fastest thing in existence, cannot escape time's warping. As it climbs away from massive objects, its energy drains, its color reddens, its rhythm slows. Gravity reshapes not only where things move, but when. If time can bend, then what does it mean for time to exist at all? Is it a fundamental ingredient of the cosmos, or a byproduct of motion and gravity? Einstein's theory suggests that time and space are inseparable, woven into one continuous entity. The universe does not contain time. It is time, sculpted by matter and energy. Every moment, from the birth of stars to the fall of an apple, is a reflection of geometry. And in that geometry, no clock is truly universal. We live inside this illusion of shared time. When you glance at your watch, it feels synchronized with the rest of the world. Yet across the universe, every clock, from pulsars spinning hundreds of times per second to photons traveling from ancient galaxies, beats to its own rhythm. There is no single cosmic tempo. Instead, there are countless rhythms, layered and interwoven, composing the symphony of space-time itself. To understand why gravity bends time, we must venture deeper, beyond the surface of familiar experience, into the mathematics that describes how the universe truly works. The secret lies not in force, but in form, in the curvature of space-time, and how matter tells it to bend. The idea that gravity bends time may sound strange, but the evidence is all around us. Every second, satellites above our heads whisper proof through their signals. The navigation system that guides an airplane across the ocean or a traveler through city streets depends on clocks synchronized to within billionths of a second. Those clocks sit both on Earth and high above it, and their disagreement would grow dramatically without the corrections demanded by Einstein's equations. Each orbiting satellite, far from Earth's center, feels weaker gravity, and its time flows faster. Down below, deeper within Earth's gravitational well, our time runs slower. To keep our technology functional, engineers must constantly bridge those two flows, uniting the sky's quickened seconds with the ground's slower beat. The difference is minute, only about 45 microseconds per day, but it is real, measurable, and relentless. Over a single day, that small drift would send navigational readings astray by kilometers. The technology of modern life survives only because our species learned to accept that time is elastic. We have built an entire civilization on top of relativity, even if most people remain unaware of it. Every text message, every guided rocket, every precise scientific instrument is calibrated to a universe where time bends. Yet this bending is not limited to the delicate machinery of satellites. It reaches into every level of existence. Deep inside the Earth, where gravity's pull is stronger, clocks would run ever so slightly slower than those at the surface. On the peaks of mountains, they would run faster. You age a little quicker at the summit of Mount Everest than in the depths of a mine. It is an imperceptible difference, but it is the same phenomenon that rules the fate of galaxies and black holes. The bending of time by gravity is universal, extending from our daily lives to the edge of eternity. For Einstein, this realization did not emerge from speculation, but from the structure of mathematics itself. He saw that, to understand gravity, one must not think of forces, but of geometry. Imagine a grid of space and time stretched taut, each line marking a direction in which things can move or moments can pass. Place a planet upon this grid, and the fabric dips, curving the lines around it. To an observer standing nearby, it feels as though an invisible force pulls them toward the planet's center, but the truth is simpler. They are following the curved paths of space-time. What we call gravity is merely the result of geometry telling matter how to move. But Einstein's revelation went even further. The curvature does not merely shape space, it shapes time. The closer one stands to a massive object, the more space-time bends inward, and the more time itself slows relative to regions farther away. A clock near a planet's surface must fight against the warping of space-time, its ticks stretched apart by the depth of the gravitational field. A clock in deep space, where curvature is gentle, ticks freely. This relationship between mass, curvature, and time was written into the Schwarzschild solution, the first exact description of how gravity distorts space-time around a spherical mass. Mathematically, it can be expressed through the ratio between the coordinate time experienced by a distant observer and the proper time experienced locally. The formula shows that as one approaches the center of gravity, the fraction diminishes, and time itself slows. Though the equation is elegant, its meaning is profound. Time is not absolute but sculpted by the structure of the universe. Every atom, every photon, every heartbeat experiences its own pace, set by its path through space-time. When we gaze into the night sky, we are not seeing the universe as it is, but as it was, because light needs time to travel. Some of the starlight reaching our eyes tonight began its journey before the first humans walked the Earth. That delay is not merely distance, it is time woven into space. The two cannot be separated. The deeper we look, the further back we peer into the past. The cosmos we see is an archive of moments frozen along different layers of time's flow. Even our own sun bends time. The photons escaping from its surface lose energy as they climb out of its gravitational field, their frequencies shifted toward red. This gravitational redshift is not merely a change in color, it is a signature of time dilation itself. The slower rhythm of clocks deep within the sun's gravitational well stretches the light that leaves it. The universe is filled with such shifts. Every massive object carries its own temporal fingerprint, marking how deeply it distorts the continuum around it. In this sense, the cosmos is a grand orchestra of ticking clocks, none of them perfectly synchronized. Near massive stars, time slows and melodies deepen. In the emptiness between galaxies, time races ahead, light flickers more quickly, and cosmic expansion stretches the fabric wider still. Our intuition rebels at the thought that time is not uniform, yet it is this very asymmetry that makes the universe dynamic. Without the differential flow of time, matter could not collapse into stars, galaxies could not form, and motion itself would lose its meaning. Each of us experiences only a small slice of this grand distortion. We walk through life believing that our seconds and minutes are universal because our senses are confined to a narrow region of space-time. But if we could step outside, hovering between planets, we would see that every world carries its own tempo. The moons of Jupiter experience time at a slightly different rhythm than their parent planet. The gravitational pull of massive worlds sculpts temporal gradients across their systems, shaping how energy flows and how orbits evolve. This truth, that time bends with gravity, invites a deeper question. If gravity can stretch or compress time, then perhaps time itself is not a background, but an active participant in the cosmos. It may not simply record events, but shape them. To understand this, we must look beyond the comforting image of clocks and gears, beyond Newton's steady tick, into the geometry of time itself, the foundation upon which all motion rests. In the early years of the 20th century, this realization changed the very language of physics. The idea that gravity and time are inseparable led to a new picture of the universe, one where the curvature of space-time replaces the invisible hand of force, and where the ticking of clocks reveals the hidden structure of reality. To imagine how gravity bends time, picture yourself floating far from any planet or star, surrounded by emptiness. Out there, your clock ticks freely. Each second feels precise and predictable, matching the beat of your heart. Now imagine descending slowly toward Earth. As gravity grows stronger, your motion through space-time changes. The closer you fall, the slower your clock ticks, compared with the one you left behind. You do not feel this slowing. Your pulse, your thoughts, and your breath all remain perfectly normal. But if a friend watching from above could see your clock, they would see its hands creeping ever more slowly as you descend. To them, you appear to be moving through time at a reduced pace. To you, they are the ones speeding ahead. This strange duality is not illusion, but fact. Both observations are correct because time itself is not universal. It depends on where you stand and how fast you move through the geometry of space-time. The deeper you go into a gravitational field, the more stretched your seconds become. What we call a second on the surface of Earth is slightly longer than a second in orbit. What feels identical locally diverges globally because every region of space-time defines its own rhythm. This is not some trick of perspective, but a reflection of reality's deepest architecture. Einstein's equations describe how matter curves space-time and how that curvature determines the motion of matter. In that relationship, time and gravity are two sides of the same coin. Mass tells space-time how to curve, and space-time tells mass how to move. When we say that gravity slows time, what we truly mean is that space-time itself tilts and warps so that the direction we call future no longer runs parallel across the cosmos. Each location's future points slightly, differently, like lines on a curved surface diverging and converging across the landscape of reality. On Earth, this warping is gentle, subtle enough that it took generations of scientists to detect it. But the same principle governs the cosmos on every scale. Near massive stars or black holes, the bending of time grows immense. A clock approaching such an object slows dramatically relative to the universe beyond. To a distant observer, it seems to freeze altogether, its final tick hanging eternally on the edge of invisibility. Yet to the falling observer, time continues normally, unbroken and unhurried. This contradiction is not an error, but a clue. There is no single objective flow of time that the universe must obey. There are only local flows, each determined by the geometry of its region. This insight forces us to rethink even the simplest notions of simultaneity. Two events that appear to happen at the same time in one place may occur at entirely different times elsewhere. The universe does not share a universal now. Instead, every observer carries their own version of the present, sculpted by their motion and their position in gravity. Time, once thought to be the same everywhere, reveals itself as a patchwork of local realities stitched together by relativity. The human mind struggles with this because our experience is narrow. We evolved under Earth's gentle gravity, where the bending of space-time is mild. Our language, our measurements, our instincts all assume that 1 second equals 1 second everywhere. Yet physics shows that this is only approximately true. If we could step onto a neutron star, our seconds would stretch into hours for those watching from afar. If we orbited close to a black hole, we could witness the entire future of the universe unfold in what feels like a single afternoon. Time itself would become distorted beyond comprehension. Even light, that eternal messenger of the cosmos, cannot escape this distortion. When a photon climbs out of a gravitational well, its frequency decreases, its energy fades, and its color reddens. This redshift is not a sign of light slowing down, for light always moves at the same speed, but a sign that time itself has changed its pace. The waves of light have been stretched by the curvature they traverse, their rhythm altered by gravity's influence on time. Through this stretching, astronomers can read the fingerprints of gravitational fields across the universe. decoding how deep or shallow those wells of time truly are. Perhaps the most haunting aspect of this discovery is its simplicity. The equations that describe time dilation are not exotic. They emerge naturally once space and time are treated as a single entity. This unity, space-time, erases the boundaries between where and when. Every movement through space is also movement through time. If you stand still in space, you move fully through time. If you move faster through space, you move slower through time. Motion and gravity intertwine so completely that they cannot be separated. They are one phenomenon seen from different angles. When Einstein presented this vision, it was more than a scientific revolution. It was a philosophical one. The steady, mechanical time of Newton was replaced by a living, malleable continuum that responds to the presence of matter. The clock on your wrist, the orbit of a planet, the flicker of a pulsar. All are expressions of the same fabric bending and evolving. Time is not a backdrop, but a participant in the cosmic dance. It stretches around massive bodies, slows near gravity's depths, and flows more freely in the emptiness between stars. This means that our sense of an orderly universe, governed by a single ticking cosmic clock, is an illusion born of limited perspective. Each point in space experiences its own passage of time, and those passages weave together into the grand story of the cosmos. The flow of time is not something that exists independently. It is the echo of geometry, the pulse of space-time responding to energy and mass. As the last century of discovery has shown, understanding this truth reshapes not only physics, but our place within the universe. We are beings made of matter, bound by gravity, and carried along by local time. The seconds we live are not universal, but specific to our corner of existence. Somewhere, on a distant world orbiting another star, time flows differently. Its people, if they exist, measure their days by clocks that tick at another rate. Yet their experience of the moment feels as real and complete as ours. In the vastness of space-time, all those rhythms coexist, overlapping like layers of music that never align perfectly yet form a coherent whole. Einstein's insight teaches us that the cosmos has no single heartbeat. There is only the geometry of existence and the endless symphony of times it creates. Gravity is not just a force that binds planets and stars. It is the sculptor of moments, the artist of duration, the reason that time does not stand still. To understand how deeply it weaves through everything we know, we must learn to see beyond space, beyond clocks, beyond even motion itself. For if gravity bends time, then what truly bends is the foundation of experience, the link between cause and effect, between past and future. To grasp how this bending works and what it means for the nature of reality, we must look closer at the geometry beneath it all. The next step in this journey lies in understanding how Einstein's mathematics turns curvature into destiny, how the very shape of spacetime determines the flow of time itself. In the winter of 1915, Albert Einstein stood before the Prussian Academy of Sciences and revealed an idea that would change humanity's understanding of the universe forever. His equations of general relativity described gravity not as a force pulling at a distance, but as the very curvature of spacetime itself. The concept was radical, even for physicists already stunned by his earlier theory of special relativity. Now time and space were no longer fixed coordinates on a cosmic grid. They were flexible, responsive, living parts of the universe's structure. Matter told spacetime how to curve, and that curvature told matter how to move. It is difficult to overstate the magnitude of this revelation. Before Einstein, space and time were thought to be distinct. Space was the stage, and time the metronome marking events upon it. But the mathematics of general relativity merged them into a single four-dimensional continuum, 3 dimensions of space interwoven with one of time. The distances between points in this continuum were measured not only by spatial separation, but by temporal difference as well. The geometry of space-time determined everything: the orbits of planets, the bending of light, the ticking of clocks. To visualize this, imagine the universe as an immense, invisible fabric. Every particle of matter, every photon of light, every heartbeat travels across this fabric along paths known as geodesics, the straightest possible lines within curved geometry. In the absence of mass or energy, space-time would be flat, and those paths would remain straight. But introduce a planet, a star, or a galaxy, and the fabric dips under its weight. The geodesics curve, guiding nearby objects into circular or elliptical orbits. To us, this curvature feels like the pull of gravity, yet nothing is being pulled at all. Objects are simply following the geometry written by mass itself. The famous image of a ball resting on a stretched rubber sheet captures part of this idea, though it is only an analogy. The true curvature of space-time is not confined to a flat surface bending downward, but occurs in every direction of space and in the flow of time. When we speak of space being curved, we must remember that the distortion of time is even more significant. Near a massive object, space contracts slightly, but time slows dramatically. The deeper you descend into a gravitational field, the slower the clock ticks compared with one farther away. This relationship can be described mathematically through the Schwarzschild solution, discovered soon after Einstein published his equations. It shows that for a spherically symmetric mass, the passage of time depends on how far you are from the center of gravity. If you are near the surface of a planet like Earth, your seconds are a little longer than those of someone floating in deep space. In words, the formula for gravitational time dilation can be expressed as the local time interval equals the distant time interval multiplied by the square root of 1 minus 2 times the gravitational constant times the mass divided by the radius times the speed of light squared. Though complex in notation, its meaning is beautifully simple. The closer you are to mass, the slower time flows. This is the geometry of time, a landscape where the rhythm of the universe depends on depth in a gravitational well. Every star, every planet, every cluster of galaxies carves depressions in the cosmic fabric. Inside those depressions, the pace of time changes. The effect is small on Earth, measurable only with sensitive instruments, but near a black hole, it becomes extreme. There, the geometry folds so sharply that time nearly stands still. To truly understand why, one must think of time not as a river flowing through space, but as one of the dimensions shaping the river's course. Imagine drawing a grid representing space and time together. Each line of constant time forms a slice through the universe's history, and each line of constant space forms a world line, the path of an object through time. In a flat universe, these lines are straight and parallel. In a curved universe, they bend toward mass. The presence of matter tilts the direction of what we call future. To move toward the center of gravity is also to move into slower time. Light, which always travels along the shortest possible route through space-time, reveals this curvature directly. When a beam of starlight passes near the sun, its path bends slightly. Astronomers observed this during the solar eclipse of 1919, confirming Einstein's prediction and proving that gravity is geometry in action. The bending of light and the slowing of time are two expressions of the same underlying truth. Mass warps the structure of space-time. Every object in motion, including you and me, follows the shape of this curved geometry. We do not feel ourselves bending through space-time because our senses are limited to our own local frame, where everything seems normal. But if we could step outside and watch the Earth from a higher dimension, we would see it tracing an elegant spiral through space-time, each rotation marking another turn in the fabric of time's curvature. Einstein's insight unified what had once been separate, space, time, and gravity, into one continuous reality. The universe became a grand geometric structure, dynamic and alive. Gravity no longer acted instantaneously across empty space as Newton believed, but propagated through the curvature of space-time at the speed of light. When a massive star moves, it sends ripples through the fabric, waves of distortion that we call gravitational waves. These ripples carry energy and information, announcing to the cosmos that matter has moved. In this way, the geometry of spacetime is not static. It flexes and trembles like the surface of a cosmic ocean. Time itself participates in those waves, stretching and contracting in rhythm with the universe's movements. For us, who experience only local time, these oscillations are imperceptible, but with instruments like the Laser Interferometer Gravitational Wave Observatory, scientists have detected them, minute variations in the distance between mirrors separated by kilometers, caused by the passage of waves that stretch and squeeze spacetime itself. Such discoveries confirm what Einstein imagined more than a century ago. The universe is geometry, and geometry is alive with time. To understand gravity is to understand how this geometry behaves, how it shapes not only motion, but the flow of existence itself. The closer we study it, the clearer it becomes that time is not something apart from space, but one of its dimensions, twisted and curved by the same forces that shape galaxies and stars. And yet, despite this profound understanding, there remains mystery. If time is part of geometry, what happens to that geometry at its extremes, near singularities where curvature becomes infinite? What does it mean for time when the structure that defines it collapses beyond recognition? These questions lead us deeper, toward the edges of comprehension, where mathematics begins to blur into philosophy, and where the geometry of time reveals its most haunting secrets. To understand how gravity shapes time, it helps to let go of the idea that space-time is a backdrop against which events occur. Instead, think of it as the stage and the play combined, a living structure that both contains and responds to what happens within it. Every mass, from a pebble to a star, distorts the fabric of space-time, bending its lines of motion and tilting the direction of time. What we experience as gravity is simply the natural tendency of objects to follow those bent lines, paths of least resistance called geodesics. Imagine a marble rolling across a stretched rubber sheet. If the sheet is perfectly flat, the marble glides straight and steady. But if you press your hand into the sheet, the marble curves toward your palm. Nothing pulls it sideways. It merely follows the surface beneath it. Replace the marble with a planet, and your hand with a star, and you have the essence of Einstein's vision. Gravity is geometry made tangible. Yet this analogy captures only half the truth, for it shows curvature in space, but not in time. The deeper reality is that time itself bends more dramatically than space does. Near massive objects, the very flow of moments slows. A second near the surface of a star is longer than a second far from its reach. This is why the clocks in orbiting satellites must be adjusted, and why the passage of time near a black hole diverges from that in open space. The geometry of space-time dictates not only where things move, but how fast time moves for them. The great power of Einstein's theory is that it makes this relationship quantitative. The curvature of space-time can be calculated, and from it, the behavior of time can be predicted. In the Schwarzschild geometry, which describes space-time around a spherical mass, one can see precisely how the ticking of a clock depends on the gravitational field. A distant observer, watching a clock deeper in the gravitational well, would see it ticking slowly, its rhythm drawn out like a stretched note in music. But to the person holding that clock, nothing feels unusual. Their pulse, their breath, their thoughts all keep pace. Each observer is right within their own frame, yet they disagree when they compare across the curve. This disagreement lies at the heart of relativity. Time is not absolute because there is no universal frame of reference. Each observer carries their own measure of duration, their own local clock, shaped by their motion and position in space-time. When two observers reunite after traveling through regions of different curvature, they discover their clocks no longer agree. One has aged more, the other less, and the difference is not illusion, but consequence. The structure of space-time itself has assigned them different paths through the river of time. To visualize how this works, physicists often speak of light cones, diagrams that show the directions in spacetime along which light and information can travel. In a region far from gravity, these cones stand upright, their sides marking the constant speed of light. But near massive bodies, the cones tilt inward, bending toward the source of gravity. The future, as defined by the direction of time's flow, leans toward mass. The stronger the gravity, the greater the tilt. Near the edge of a black hole, the cones tilt so steeply that every possible future points inward. Once an object crosses that boundary, it can no longer move outward through space without moving backward through time, which nature forbids. This is why nothing escapes a black hole. It is not that gravity pulls with infinite strength, but that the geometry of time itself has been folded inward. The realization that geometry controls destiny is one of the most beautiful aspects of general relativity. The universe, vast and dynamic, behaves like a grand clockwork, whose gears are not mechanical but geometric. Every motion, from the orbit of planets to the fall of an apple, follows the contours of space-time. The curvature around the Sun guides Earth into its nearly circular path, and the curvature near a galaxy cluster bends the light of distant galaxies into luminous arcs, a phenomenon we call gravitational lensing. These cosmic lenses reveal not only the distribution of matter, but the very shape of space-time itself. We can even see time's curvature imprinted on the cosmic background radiation, the faint afterglow of the Big Bang. Tiny variations in temperature across the sky trace the distribution of matter that shaped space-time in the early universe. Where the gravitational wells were deep, time flowed more slowly, freezing fluctuations in patterns we can still detect today. The geometry of time has left fingerprints on the oldest light in existence. In our daily lives, these distortions are too small to notice, yet they never vanish. Each step you take alters your position in space-time, changing your clock's rate by a minuscule amount. Your head, being slightly farther from Earth's center than your feet, experiences time a little faster. Though the difference is unimaginably small, it exists, and it means that even within your own body, time is not perfectly uniform. Every molecule, every neuron, every heartbeat occurs within its own subtly different flow of moments. This realization can feel disorienting, yet it is profoundly unifying. It means that all of existence, from galaxies to human thoughts, shares a single underlying geometry. Time is not a mystery hovering outside the laws of physics. It is a manifestation of those laws. The slowing of a clock near Earth's surface and the bending of light around a distant quasar are governed by the same equations. The universe speaks one language, and that language is geometry. Einstein once said that the happiest thought of his life came when he realized that a person in free fall does not feel gravity. Inside a falling elevator, you would float weightless, your watch ticking normally, your heart steady. You would feel as though gravity had vanished, yet to an outside observer, you are plunging through curved space-time. Your trajectory determined entirely by the geometry beneath you. That simple insight, that free fall and curved geometry are equivalent, became the cornerstone of general relativity. It revealed that gravity is not something added to space-time, but an expression of its shape. From that shape arises everything we call motion. Planets orbit stars not because they are pulled by an invisible hand, but because they are following geodesics through the curved geometry that mass creates. The closer they move toward the center, the slower their time flows relative to distant observers. Each orbit is a dance between space and time, between motion and duration. And through this dance, the universe reveals its symmetry, a harmony between geometry and existence itself. But if gravity can bend time, what happens in the strongest gravitational fields, where curvature becomes extreme? What does the geometry of time look like at the edge of a black hole, where the future tilts so sharply it nearly folds back upon itself? To find those answers, we must follow the curve deeper, to the very brink of space-time's endurance. The deeper we journey into gravity's domain, the more profoundly the geometry of time reveals itself. To approach a massive object is to walk uphill through time's own landscape, where each step stretches the seconds around you. The curvature of space-time is not visible to the eye, yet it shapes every movement, every orbit, every photon that travels through the cosmos. What we sense as the pull of gravity is the natural tendency of everything to follow the easiest possible route through this geometry. A route that feels curved in space, but straight within the four-dimensional continuum of space-time. Einstein's equations capture this relationship in a form both elegant and terrifying in its depth. They show that the distribution of energy and matter determines the curvature of space-time, and that curvature dictates the motion of matter and light. The equations are a dialogue between geometry and existence, a cosmic feedback loop in which space, time, energy, and motion speak to one another continuously. The universe does not merely exist within space-time. It is space-time, constantly reshaping itself in response to what it contains. If we could watch the flow of time from above, we would see it as a vast ocean, undulating and rippling under the influence of gravity. Around stars and planets, gentle depressions form. Around neutron stars and black holes, the ocean plunges into abyssal chasms where time slows almost to a halt. Light that ventures near those depths bends sharply, its path distorted by the curvature, and its frequency redshifted as it climbs out again. The slower flow of time near the surface of massive bodies is not a mechanical delay, but a change in the structure of reality itself. In the language of relativity, every object follows a world line, its path through space-time from past to future. Your own world line stretches from the moment of your birth to your final breath, an unbroken line that curves gently through the gravitational well of Earth as the planet moves around the Sun. The shape of that line determines how much proper time you experience, your personal measure of duration. Another person moving differently through the universe traces a slightly different world line, and when those lines meet again, they reveal how time has diverged between them. The greater the difference in motion or gravitational depth, the greater the difference in experience time. This concept lies at the heart of the twin paradox. Imagine one twin remaining on Earth while the other travels into deep space at tremendous speed, then returns. Upon reunion, they find that less time has passed for the traveling twin. Motion through space affects motion through time, and the geometry of space-time ensures that both experiences remain self-consistent. Each twin lived a complete and normal life, yet their world lines curved through different regions of the cosmic fabric. Gravity and acceleration, both manifestations of curvature, define how long each journey feels. On cosmic scales, the same geometry governs the movement of galaxies and the expansion of the universe itself. The great arcs of galaxy clusters, the bending of starlight, and the time delays observed in gravitational lenses are all signatures of space-time curvature. Even the background radiation left from the Big Bang carries the imprint of geometry, slight irregularities that grew into galaxies under gravity's guidance. Everywhere we look, time and space bear the fingerprints of mass and energy. When scientists first detected gravitational waves, ripples traveling through space-time at the speed of light, it was as though the universe had spoken in its native tongue. These waves arise when massive objects, such as black holes or neutron stars, spiral together and merge. The collision disturbs space-time itself, sending vibrations across the cosmos. As a wave passes through Earth, it momentarily stretches and compresses distances, altering the rate at which time flows by the tiniest fraction. The effect is unimaginably small, smaller than the width of a proton, yet measurable. Each detection confirms that the geometry of time is not static but dynamic, alive with motion. If we think of space-time as a vast four-dimensional fabric, then gravity is the texture woven into it, and time is the tension that gives it form. The greater the mass, the tighter the weave, the slower the rhythm of passing moments. Near the event horizon of a black hole, the geometry stretches toward infinity, and time becomes almost frozen relative to the outside world. To an observer falling inward, nothing unusual occurs. Their clock ticks normally as they cross the horizon. But to an observer far away, those final seconds take forever. The two realities coexist, each complete within its own geometry, yet forever separated by curvature. The realization that time can stretch to near infinity shows the extraordinary power of geometry. It means that the very concept of before and after depends on where you stand in space-time. In extreme gravity, time behaves like a landscape folded so sharply that one traveler might climb endlessly toward a horizon that can never be reached, while another experiences that crossing as effortless. Einstein's equations do not break here, they simply reveal that geometry has limits beyond which our ordinary sense of sequence dissolves. Even in the calm emptiness between stars, space-time is never perfectly flat. The gravity of distant galaxies, the subtle pressure of dark energy, and the motion of the universe's expansion all contribute to its shape. The geometry of time extends across the cosmos like a network of invisible valleys and ridges, guiding light and matter through their eternal dance. When we observe light from distant quasars delayed or magnified by intervening galaxies, we are watching time itself bend across billions of light years. This picture changes how we think of cause and effect. In Newton's world, forces acted instantaneously, pushing and pulling objects across space. In Einstein's world, the geometry of space-time determines what can influence what. Nothing can move faster than light because the structure of space-time forbids it. Time and causality are built into the geometry. Every event lies within a cone of possible futures, and the tilt of that cone depends on gravity. Near massive bodies, the cone narrows, limiting how quickly signals can escape. In this way, gravity not only shapes the flow of time, but the very structure of possibility. When you look up at the night sky, you are looking across that structure. The starlight that reaches your eyes has traveled through regions where time flowed at different rates, where curvature shifted and evolved. Each photon carries a history of the geometry it traversed. In its faint glow lies the story of space-time's architecture, written not in words, but in frequency, energy, and delay. The universe, then, is not built from things alone, but from the relationships among them, the geometry that binds energy, matter, and time into one inseparable whole. Every atom is a note, every orbit a rhythm, every moment a vibration in the grand composition of space-time. To understand the geometry of time is to understand that existence itself is motion through curvature, that being and becoming are the same. And so the lesson of Einstein's geometry is not simply that gravity warps time, but that time is gravity's expression. Wherever mass exists, time bends. Wherever energy flows, curvature follows. The shape of the universe is the shape of time. To explore this further, we must turn from the grand equations back to our home, to Earth itself, where the bending of time is subtle but real, measurable, and woven into the technology that sustains our modern world. High above Earth, a fleet of satellites drifts in precise orbits, each carrying a clock so accurate it can measure a billionth of a second. They circle silently, their signals crisscrossing the planet below, guiding ships, planes, phones, and the quiet footsteps of travelers who never see them. Every moment, they mark the rhythm of Earth's invisible heartbeat, the network of time that synchronizes the world. Yet the satellites' clocks do not keep perfect agreement with those on the ground. They run faster, gaining about 45 microseconds each day. To the untrained mind, this difference seems trivial, but to the universe, it is everything. It is the whisper of gravity bending time. If engineers ignored this effect, the global positioning system, the web of timing signals that lets us find our location anywhere on Earth, would drift. Within minutes, navigation would fail. Within hours, the system would collapse. Every GPS receiver, from aircraft guidance to phone maps, depends on corrections born from Einstein's theory of relativity. Without accounting for the slowing of time in stronger gravity, the satellite's signals would betray us. The Earth itself teaches us that time is not constant. It changes with height, motion, and mass. On the surface, we live deep within Earth's gravitational field. Our planet's mass curves space-time around it, pulling everything inward and slowing the flow of time relative to open space. A clock placed on a mountaintop runs slightly faster than one at sea level because it lies a little farther from the planet's mass. The difference is tiny, just a few nanoseconds per day, yet it is real and measurable. Mountain climbers age ever so slightly faster than those who dwell by the ocean, not by choice or destiny, but by geometry. The first proof of this phenomenon came not from satellites or astronauts, but from a small tower on Earth. In 1959, physicists Robert Pound and Glenn Rebka performed an experiment at Harvard University. They sent gamma rays up and down a vertical shaft inside a building, measuring the change in energy caused by gravity. The light traveling upward lost a minute fraction of its energy, as if climbing out of a well. It was the first direct detection of gravitational redshift, the stretching of light and time by gravity's pull. Their result confirmed what Einstein had predicted decades earlier. Time runs slower in stronger gravity. This slowing is not a metaphor. It is a measurable distortion of reality. Near Earth's surface, the effect is weak, but its precision grows with our ability to measure it. In modern laboratories, atomic clocks so accurate they lose less than 1 second over the age of the universe can detect time differences over a height of less than 1 meter. When one clock is lifted to a shelf above another, it ticks slightly faster, not because of mechanics or calibration, but because it exists in a region of weaker gravity. We live within a gentle gradient of time, stretched and compressed by Earth's mass beneath our feet. If we could see the geometry of space-time made visible, we would perceive Earth surrounded by invisible contours of duration, like ripples frozen in glass. Each contour would mark a different rate of time's passage. On the surface, where gravity is strongest, the lines crowd closely together. Farther away, they spread apart. To orbiting satellites, time flows more freely, the seconds lengthening slightly compared to hours. Yet every clock, whether in space or on the ground, believes it is ticking normally. There is no absolute measure to reveal whose time is correct. Each clock, each observer, experiences its own reality. Einstein's insight was that both perspectives are valid because time is not separate from space. The two are bound together into a single entity, space-time, whose curvature determines the behavior of all things within it. Gravity is not a force acting through emptiness, it is the geometry of that curvature itself. When we feel our weight pressing downward, we are not being pulled, we are being guided along curved lines in space-time, lines that tilt slightly toward the planet's center. Our bodies, our instruments, even our thoughts, unfold along those tilted lines of time. The Earth, massive though it seems, warps space-time only gently. The dilation of time near its surface is minute, roughly 1 part in a billion compared to outer space. But the principle extends everywhere, scaling with mass. A neutron star, the collapsed core of a once luminous giant, has a gravity so fierce that time on its surface runs hundreds of thousands of times slower than in interstellar space. Near a black hole, time slows almost to a halt. The same mathematics that governs satellites above Earth also governs the horizons of eternity. The difference is only in degree. For us, the slowing of time on Earth remains mostly hidden. We live inside it, our clocks synchronized by convention, our senses too coarse to detect relativity's subtle drift. Yet every breath we take occurs in a gravitational field that stretches time differently from place to place. The seconds we count are not universal but local, shaped by Earth's curvature. Even our planet's center, buried beneath kilometers of rock, experiences slightly slower time than its surface. If we could compare a clock there to one in orbit, the difference would accumulate, tiny but real, across the ages. From this perspective, our everyday world becomes part of a cosmic symphony. Time does not march uniformly from past to future. It flows unevenly, rising and falling with the topography of gravity. Each object, each altitude, carries its own rhythm. The global positioning satellites, high above the surface, sing a faster tempo. The oceans, held close by gravity's embrace, hum a slower one. Our planet's mass composes a quiet harmony of clocks, each playing a slightly different note in the melody of space-time. This delicate difference reminds us that absolute time, the universal ticking imagined by Newton, does not exist. What we call now is a local condition, a patch of geometry defined by our motion and our gravity. When astronauts journey into orbit, they move not only through space but through time itself, entering a region where seconds flow differently. Upon returning to Earth, their clocks disagree with those left behind, not from error but from nature's design. Time is flexible, and Earth's gravity stretches it. If we could hover far from our planet, watching it spin below, we would see more than clouds and continents. We would see a slow distortion of time itself, an immense sphere of warped duration surrounding a world of oceans and light. Every signal we send upward, every photon escaping Earth's gravity, carries the signature of that warping, a slight shift in frequency, a faint elongation of energy. The universe does not allow time to pass freely near mass. It bends it, stretches it, and weaves it into the fabric of motion. In this way, the slow time of Earth becomes our anchor to reality. It keeps us grounded not only in space, but in history. Every clock on the planet is part of a deeper continuum, a flow sculpted by Earth's presence. The next time you look at your watch, remember that it is not merely counting seconds. It is tracing the shape of the world beneath you, keeping rhythm with the curvature of space-time itself. And as we look upward, beyond the atmosphere and the orbiting satellites, we realize that these subtle distortions are only the beginning. For every slight bending of time on Earth is a whisper of something far greater, the immense warping that awaits near black holes, where time slows until it nearly stops. To understand the true depth of this phenomenon, we must follow time to its edge, where gravity's hand closes fully around it, and the flow of existence itself begins to fracture. When you fall, it feels like gravity is pulling you. The ground rushes upward, air presses against your skin, and the world accelerates around you. But to Einstein, falling means something entirely different. In his geometry of the universe, a falling body is not being pulled at all. It is simply following the natural curve of space-time, a path known as a geodesic. To fall is to move freely, unforced, through the curved fabric shaped by gravity. The feeling of weight disappears because you are no longer resisting that curve. You are riding it. Imagine stepping off a cliff into pure emptiness. For a moment, before the wind roars, you feel weightless. Your stomach lifts, your muscles relax, and the sensation of being pulled down vanishes. This is the essence of free fall. You are not being forced, you are simply moving along space-time's natural geometry. Einstein called this realization the happiest thought of his life, for it revealed that gravity and acceleration are two faces of the same truth. What we experience as a force is only the resistance to free motion through curved space-time. In the language of relativity, every object travels through space-time along a world line, its own unique path through the continuum of existence. When an object is free from all external forces, its world line follows a geodesic, the straightest possible path in a curved geometry. If you stand still on the ground, your body is not following that natural path. The ground beneath you pushes upward, preventing you from moving along space-time's curve. You feel the weight of that resistance as gravity. But the astronaut orbiting above, floating weightless, feels nothing. because they are in continuous free fall. They move forever along a geodesic, falling around Earth rather than into it. This idea changes everything. Gravity is not a mysterious tug from a distance. It is the shape of the universe itself. The astronaut's orbit, the apple's fall, and the motion of planets are all expressions of geometry. Each follows spacetime's curves, shaped by the mass beneath them. The feeling of being pulled arises only when something interrupts that motion, when the ground or a spacecraft or any solid surface resists the natural trajectory. Remove the resistance, and gravity vanishes from experience, even though spacetime's curvature remains. To picture this, imagine spacetime as a vast, invisible river. The flow of the river represents the natural paths of motion, the geodesics. When you are in free fall, you drift with the current, unaware of its pull. When you stand on the shore, resisting the flow, you feel the pressure, the sensation we call weight. The current never changes. It is your interaction with it that defines what you feel. In this river, space and time flow together, and the currents bend around every mass in the universe. If you were to fall freely toward Earth from high above, your experience would be strangely peaceful. In your local frame, nothing changes. You float beside the objects you dropped with you. They neither rise nor fall relative to you. You could hold out your hand and catch them effortlessly. From your perspective, gravity seems gone, yet to an observer standing safely on the ground, you and your objects accelerate downward at the same rate, drawn along the planet's curvature. Both experiences are true, reconciled by the geometry of space-time. Now imagine a more extreme descent, falling toward a massive planet, or even a star. As you approach, the curvature of space-time deepens, and time itself slows relative to distant observers. Your watch continues to tick normally, your heart beats in rhythm, your thoughts unfold at their usual pace. But if someone watching from far away could observe your clock, they would see it run slower and slower as you fall. Every pulse of light you emit would reach them stretched, its wavelength longer, its frequency lower. The deeper you fall, the more your light shifts toward red, a phenomenon known as gravitational redshift. It is not merely light that slows, but time itself. This redshift has been observed countless times across the cosmos. Photons climbing out of gravity's wells lose energy, as if struggling against time's stretching. The light from the surface of the sun, when measured precisely, is slightly redder than the same light produced in laboratories on Earth. Near denser objects like white dwarfs or neutron stars, the effect is magnified. Light escaping their surfaces emerges drained, its rhythm slowed by spacetime's curvature. Every beam of light in the universe is a traveler through the geometry of time, its color and frequency shaped by the path it takes. The connection between free fall and time dilation reveals something profound. When you fall through spacetime, you are not moving through an external stage. You are part of the stage's shape. Your trajectory, your aging, and even your perception of cause and effect are determined by geometry. You experience your own time as normal, yet to the rest of the universe, that same time flows differently. In a sense, every fall is also a journey through layers of time. The astronauts circling Earth live this truth daily. Their spacecrafts orbit because they are constantly falling, not down, but around. They follow the planet's curve precisely, so that as Earth pulls them inward, their forward motion carries them around it. They are in perpetual free fall, suspended within spacetime's geometry. Inside the cabin, pens float, hair drifts upward, and hearts beat in a weightless calm. But their clocks, though ticking normally to them, run faster than clocks on the surface, where gravity is stronger. They age slightly quicker, by microseconds each day, than those bound to the ground. Time dilation accompanies every orbit, a silent passenger carried along the curve. If we could extend this journey, falling farther and deeper into stronger gravitational fields, we would see time slow more dramatically. Near a black hole, where spacetime's curvature becomes almost vertical, an outside observer would see a falling traveler's motion slow until it nearly stops. The light from their ship would fade, stretched into darkness, frozen at the edge of visibility. To the traveler, though, nothing unusual happens. They cross the invisible boundary smoothly, unaware that the universe outside has leapt far into the future. This paradox, the coexistence of normal experience and infinite delay, is one of relativity's most haunting consequences. It shows that time is not a shared river flowing the same for all, but a network of individual streams, each following its own curve through space-time. Gravity shapes those streams, creating regions where moments linger and regions where they race ahead. To fall freely through space-time is to glide along those curves, feeling no force, yet traversing a landscape where time itself bends beneath you. And so the act of falling becomes a journey, not just through space, but through time. Each descent carries you deeper into slower moments, into thicker layers of existence. The farther you fall, the longer each second becomes, until at last, near the universe's most extreme gravitational wells, time stretches almost infinitely. There, gravity no longer merely bends the path of motion. It reshapes the meaning of the word future. To fall freely through space-time is to experience perfect surrender to geometry. The moment you release yourself from all support, the sensation of gravity fades, and the only law that guides your motion is curvature. You no longer resist space-time's shape. You become part of it. This is why astronauts drifting through orbit feel nothing at all, even though Earth's gravity still governs every heartbeat of their journey. They are falling endlessly and effortlessly along the contours that gravity creates. Einstein's happiest thought, that a person in free fall feels no gravity, unlocks one of the most profound truths about the universe. Gravity is not a force acting upon you, but the shape of the stage on which you move. When you fall, you move through that shape as naturally as light crossing empty space. It is only when something halts that motion, a flaw, a planet's surface, a moment of resistance, that gravity makes itself known. The pressure of the ground pushing upward against your feet is not gravity itself, but your defiance of it. The same idea governs everything that moves under the influence of gravity. The moon does not orbit Earth because it is tethered by an invisible rope. It orbits because it is forever falling. Its forward momentum carries it around the planet as the curvature of space-time guides its path. If Earth were to vanish, the moon would fly straight, following its geodesic through uncurved space. With Earth present, that straight line becomes a graceful circle, not drawn by force, but carved by geometry. In this view, all motion is communication between matter and space-time. Matter tells space-time how to curve, and space-time tells matter how to move. This dialogue unfolds everywhere, from the fall of a leaf to the spiraling of galaxies. Even light, which has no mass, listens to this conversation. It always travels at the same speed, yet its path bends in the presence of curvature. That bending is not a deviation from nature's rule, but the rule itself. Light follows space-time's geodesics. The bending of light by gravity was first confirmed in 1919, when astronomers observed starlight passing near the sun during a total eclipse. The light's path bent exactly as Einstein predicted, shifting the apparent position of the stars by a small but measurable amount. It was the first time humanity had witnessed the warping of space-time directly. The result astonished the world. Newspapers declared that Newton's universe had fallen, replaced by Einstein's curved reality. The proof was not philosophical but visible, etched in the light of distant suns. Light's behavior reveals something deeper than curvature alone. As it climbs out of a gravitational well, it loses energy. Not because it slows down, for light never changes its speed, but because the structure of time itself changes. The intervals between its wave crests stretch. To an observer at a higher altitude, the light appears redder, its frequency lower, This gravitational redshift shows that time runs slower in deeper gravity. The effect is gentle near Earth, but immense near compact stars. A photon leaving a neutron star must struggle through such intense curvature that its frequency drops dramatically before reaching interstellar space. Its color becomes a direct measure of time's distortion. You could think of spacetime as a landscape of invisible wells. Each massive body carves its own indentation, shaping how time flows nearby. When you fall towards such a well, you are simply following the downward slope of time's geometry. To move upward is to climb against it, to slow your rhythm relative to those above. The universe is filled with these gradients, smooth near planets, sharp near stars, and infinitely deep at the edge of black holes. If we could map time as a topographical surface, Earth's well would appear shallow compared with the Sun's, and the Sun's shallow compared with the crushing depth of a black hole. The deeper the well, the slower the passage of proper time. For those trapped near the edge of a black hole, the difference becomes so great that from an outside perspective, their clocks nearly stop. Every fall toward gravity's heart is a fall towards slower time. The concept of a geodesic explains this elegantly. A geodesic is the straightest possible path through space-time, though it may appear curved in space. When you throw a stone, its trajectory arcs because space-time near Earth is curved. The stone follows the geometry. You perceive the curve. The same holds true for everything that moves freely, from satellites to starlight. The beauty of this idea lies in its universality. One law governs all motion, whether it is the drift of dust or the orbit of worlds. Inside a freely falling frame, time feels perfectly ordinary. You could conduct experiments, measure distances, drop objects, and find no sign of gravity. Everything around you would float in harmony. Only by comparing your frame with another, one that resists gravity's pull, would differences in time appear. That comparison is the essence of relativity. Each observer carries their own truth, each bound by their region of space-time. This duality leads to one of the most remarkable paradoxes in physics, the simultaneous normalcy and distortion of time during free fall. To you, time feels smooth and steady as you fall. To someone far away, your time slows, your light stretches, and your motion seems to freeze as you approach stronger gravity. Both perspectives are real. The laws of physics ensure that each observer's measurements are consistent within their own frame, even if they disagree about what they see. Near the surface of Earth, the difference is too small to matter, but near extreme masses, it defines reality. For a spacecraft approaching a neutron star, the dilation of time becomes so strong that seconds for the crew could correspond to hours or days for distant observers. If the ship continued toward a black hole, this disparity would grow until communication itself became impossible. To those aboard, the journey continues normally. To those outside, it appears to slow endlessly. In this way, the act of falling reveals the true unity of gravity and time. The closer you move toward mass, the slower your clock runs. The faster you move through space, the slower you move through time. The two effects intertwine until they become indistinguishable. Gravity, motion, and duration are not separate things, but expressions of one geometry. To understand one is to understand them all. Einstein's equations describe this geometry with relentless precision, yet their simplicity conceals their wonder. They show that if you know how matter and energy are distributed, you can determine the entire structure of space-time. How it curves, how it flows, how it tells time. Every fall, every orbit, every flicker of starlight is a chapter in this cosmic geometry. But as we follow these curves deeper, the story grows stranger. What happens when the curvature becomes so great that light itself cannot escape? When time slows, not just relatively, but absolutely, freezing the flow of moments from the perspective of the universe beyond. The answer lies in the most mysterious objects known to physics, the black holes. where falling through space-time becomes a fall beyond time itself. To fall through space-time is to drift along the most natural line the universe can offer. No engines, no fuel, no effort. Only motion written into the geometry of existence itself. A leaf descending through the air, an asteroid spiraling toward a star, or a body tumbling through the silence between worlds. All are obeying the same law. They are following geodesics, the straight lines of a curved reality. Gravity does not drag them downward. It simply allows them to follow the only path that space-time permits. In the emptiness between galaxies, where space-time flattens almost completely, these paths appear straight. But near any mass, the geometry tilts, and those paths bend inward. Space and time, woven together, form a landscape that pulls everything into its curves. If you could see this landscape made visible, if the fabric of space-time glowed faintly like mist under moonlight, you would see every planet, every star, every galaxy sculpting depressions and valleys into that invisible surface. You would watch photons slide through those valleys like water, curving as they go. And you would understand that what we call falling is simply the motion of things along the downward slopes of time itself. The beauty of this truth lies in its quiet inevitability. The universe needs no external force to govern its movement. Geometry alone is enough. Where space bends, objects move. Where time tilts, moments stretch. The same equations that guide the orbit of a moon also guide the flow of seconds near a mountain peak. Gravity is not a separate entity acting upon the cosmos. It is the shape of the cosmos. From this perspective, falling becomes more than motion. It becomes a revelation of time's structure. Every object that moves freely through space-time experiences its own proper time, ticking steadily along its path. The deeper it moves into a gravitational well, the slower that time flows relative to distant observers. The curvature of space shapes the trajectory, but the curvature of time defines how long the journey feels. The two are inseparable. Imagine yourself floating in orbit, then slowly lowering toward Earth. To you, everything seems normal. You feel no force, no resistance, no slowing. Your clock ticks, your heartbeat continues, and your senses perceive steady flow. Yet to someone watching from above, your descent appears slightly delayed. Your clock runs slower, your signals stretch in frequency, your seconds lengthen. As you fall deeper, the difference grows. The further into gravity's well you go, the more your time diverges from theirs. And yet both of you exist truthfully within your own timelines, both bound by the same laws. This dual nature of reality, the coexistence of local normalcy and external distortion, is one of the most profound consequences of relativity. It tells us that time is not an absolute quantity shared across space, but a local dimension sculpted by motion and gravity. Every observer carries a private version of history, unfolding at a rate defined by their position within space-time's curvature. In that sense, each consciousness is a separate rhythm in the universal orchestra. Now imagine a stronger field, a descent not toward Earth, but toward a neutron star. The star's gravity is immense, its curvature extreme. As you fall, the pull grows fierce. The light from the star above you, blue, shifts into brilliant intensity, and the light from the universe beyond dims into deeper red. To you, seconds still pass normally, but to any distant observer, your descent seems to slow. As you approach the surface, their measurements show your time stretching longer and longer. If you could send them a signal every second by your clock, they would receive each one delayed, arriving farther apart until, near the surface, the intervals approach infinity. This is the experience of falling through steep space-time curvature. For the traveler, continuity; for the observer, eternity. Both are true because time itself is part of the geometry being traversed. When gravity deepens, time bends so severely that one perspective cannot map cleanly onto another. To reconcile the two requires Einstein's equations, the mathematical bridge across perception. The same process unfolds across the universe wherever mass distorts spacetime. Stars curve it gently, galaxies bend it broadly, and black holes twist it almost to breaking. Falling towards such regions is falling into the depth of time itself, a journey not merely downward in space, but inward in duration. The closer one approaches a black hole's event horizon, the slower their clock runs relative to the cosmos. The flow of time becomes viscous, resisting progress, as if the universe itself were stretching the seconds apart. From a safe distance, an observer watching this fall would never see the traveler cross the event horizon. The traveler would appear to slow, to fade, and finally to freeze, their last image suspended on the edge forever. Light from their ship would redden, weaken, and vanish as its wavelength stretched beyond visibility. To the observer, time at the horizon stops. But for the falling traveler, time continues naturally. They pass the horizon unhindered, experiencing no wall, no boundary, only the continuation of the fall, deeper into spacetime's fold. This paradox is not contradiction, but consequence. Relativity teaches that simultaneity itself dissolves in strong gravity. What is now for the falling traveler is not now for the distant observer. Time's sequence depends on where you stand. The universe contains many overlapping versions of the present, each defined by its curvature. In this sense, every fall is a journey through different futures. When you fall toward a massive body, the geometry tilts the light cones, the possible directions that cause and effect can travel, downward. As they tilt, the range of possible futures narrows. Near a black hole, those cones tip so steeply that every future points inward, toward the center. No force pulls you there. The geometry simply allows no other path. To fall is to follow the direction time itself demands. The beauty of this realization lies in how it connects the personal with the cosmic. The same principle that governs an astronaut's orbit explains the fate of stars and galaxies. When a massive star exhausts its fuel, nothing remains to resist the inward curvature. It collapses not because gravity crushes it, but because space-time itself directs it inward. The star falls freely, obeying the same geodesic principle that guides a pebble's descent, until its matter folds into a region where geometry becomes so steep that time nearly ceases. The act of falling, then, is a bridge between worlds. On one side lies the gentle curvature of planets and stars, where time bends softly and life can thrive. On the other lies the extreme geometry of black holes, where falling becomes a one-way journey into time's deepest shadow. The transition between them marks the limit of our understanding, the point where relativity itself begins to strain. To grasp what happens beyond that threshold, we must follow the fall to its conclusion. We must ask what time becomes at the edge of forever, where even light cannot escape, and the flow of moments collapses into stillness. The answer lies in the next frontier, the domain where gravity and time merge completely, and the geometry of space-time reveals its most astonishing secret. There are places in the universe where time nearly stops, where seconds stretch into eternities, and the rhythm of existence slows to a whisper. To venture near such a place is to approach the edge of forever, the domain of black holes, where gravity's power becomes so absolute that even light cannot escape. These are not merely objects, they are regions of space-time itself, folds in the fabric of reality, where geometry bends into depths so steep that time and space exchange their roles. Here, gravity does not just pull, it reshapes the meaning of time. To understand this transformation, imagine falling towards such an abyss. At first, the experience is serene. From afar, a black hole appears small, silent, and unassuming, a dark sphere surrounded by the faint glow of distant stars. Yet as you draw closer, the light begins to change. The stars behind you distort, curving around an invisible boundary. Their images twist into rings and arcs, reflections of light bending through extreme curvature. You are not being pulled by a force. You are sliding along spacetime's steepest slope. The geometry itself directs you inward. As you descend, time begins to slow. To you, nothing feels different. Your clock ticks steadily. Your heartbeat keeps its pace. But to an observer far away, your seconds stretch longer and longer. The light from your ship climbs out of the gravitational well, losing energy with every photon, its frequency falling into redder tones. Your image dims, fading into infrared, then radio, until it disappears entirely. From the outside, it seems as though you have frozen at the edge of the black hole, trapped in perpetual approach, never quite crossing the boundary. This illusion is not caused by distortion of sight, but by the geometry of time itself. The boundary you approach is called the event horizon, the surface beyond which escape is impossible. It is not a wall or a barrier, but a horizon in the truest sense, a limit to what can be seen or influenced. Once crossed, all possible paths through spacetime lead inward. Even light, which defines the fastest possible route, finds that every direction points deeper. Inside, the future itself curves toward the center. To fall through this horizon is to move into a region where space and time exchange their identities. What was once outward in space becomes forward in time. You cannot turn back, not because of force, but because time itself no longer allows it. From the viewpoint of distant space, the black hole's clock appears to stop. Time outside and inside no longer share meaning. What takes you moments to experience may take eternity to unfold for the universe beyond. This divide between perspectives, one of relativity's most haunting truths, is not contradiction, but consequence. Each observer measures time within their own frame, and in the warped geometry near a black hole, those frames diverge completely. At the heart of every non-rotating black hole lies the Schwarzschild radius, the precise distance from the center at which the escape velocity equals the speed of light. The equation that defines it is simple, yet immense in implication. 2 times the gravitational constant multiplied by the mass, divided by the square of the speed of light. Increase the mass, and the radius expands proportionally. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it would be less than a centimeter. This means that if you compress the entire planet into a marble smaller than your thumb, its gravity would trap even light. The geometry of space-time around such a mass would twist so steeply that no path could lead outward. The strange thing is that the curvature described by Einstein's equations remains smooth across the event horizon. To a falling observer, nothing extraordinary happens there. You pass the boundary without sensation, unaware that the universe outside now sees you as frozen in time. Inside, however, the curvature grows stronger with every step. Space contracts, time slows further, and all paths lead to a central singularity, a point of infinite density where known physics ceases to apply. The equations predict a place where spacetime's curvature becomes infinite, where the concept of time itself loses definition. But is the singularity truly real, or is it a signal that our understanding breaks down? Most physicists believe it is the latter, that at such scales, quantum gravity must intervene, replacing the singular point with something finite yet exotic. The classical geometry of relativity reaches its limit, and beyond that limit, time as we know it may dissolve into something deeper, perhaps even giving rise to new dimensions of evolution. The black hole, then, is not only an end, but a beginning, a place where the laws of physics confront their own horizon. Outside the horizon, the effects of time dilation ripple outward, shaping the universe around it. Gas swirling near the edge glows with ferocious intensity, heated by friction and tidal forces. These accretion disks shine brighter than entire galaxies, releasing energy as matter spirals inward. Yet even this light carries the mark of gravity's influence. Its flickers slow, its colors stretch, its patterns delay. Astronomers observing such systems measure the warping of time itself in the rhythm of the light. If you could hover safely just above the event horizon, supported by unimaginable energy, you would see the universe in fast forward. The distant cosmos would appear to race ahead, its stars forming and dying in seconds. The expansion of the universe would accelerate before your eyes. While your own seconds pass normally, the outside world's clock races beyond comprehension. This is because time flows differently in different gravitational potentials. The deeper you are in the well, the more the rest of the universe accelerates around you. In this way, gravity allows glimpses of eternity compressed into moments. For the traveler falling freely through the horizon, this effect reverses. You would see the universe outside slow and fade. The stars would dim, their light stretched to invisibility. Communication with the outside would become impossible, not because of distance, but because time itself no longer aligns between frames. You are no longer part of their future. You have entered a region where all future points inward. The black hole consumes not matter, but causality itself. In some ways, black holes are time machines, but only one-way machines, leading always forward into deeper gravity, never back. The closer one moves toward the singularity, the more time and space intertwine until they become indistinguishable. The journey inward is not a movement through space, but through moments themselves. It is as if the traveler is being drawn into the very geometry of time, toward the point where time's arrow ends. Rotating black holes, described by the Kerr solution, complicate this picture further. Their spin drags space-time around with them, twisting the geometry into a whirling vortex. Within a certain region called the ergosphere, nothing can remain stationary. All things are forced to rotate with the black hole's spin. In this swirling geometry, time and space exchange not just direction but meaning. Theoretical trajectories suggest that under extreme conditions, such regions could even allow travel to other parts of space-time. Though in practice, such paths would be destroyed by tidal forces long before they could be completed. Still, the mathematics hints that black holes may be more than cosmic endpoints. They could be bridges, Einstein-Rosen bridges, tunnels through space-time connecting distant regions, or even separate universes. Whether such bridges truly exist remains uncertain. The equations permit them, but stability is another matter. Quantum effects likely destroy such tunnels as quickly as they form. Yet even the possibility reveals something profound, that in the universe's most extreme curvature, time and space lose their individuality, merging into a single malleable entity. Black holes are not voids, but geometrical constructs, frozen pockets of space-time whose boundaries define where time stands still. For the cosmos, they play a paradoxical role. They are destroyers and archivists alike. When a star collapses into a black hole, it carries its mass, angular momentum, and charge inward. But the information describing its finer structure seems to vanish. This apparent loss led to one of the greatest puzzles in modern physics, the information paradox. According to quantum theory, information can never be truly lost. According to classical relativity, the black hole hides it forever. Resolving this conflict may require a new understanding of time itself, a deeper theory where space-time and quantum mechanics are united. Recent discoveries suggest that black holes are not entirely silent. They emit radiation, a faint thermal glow, now known as Hawking radiation. This arises from quantum fluctuations near the event horizon, where pairs of particles spontaneously appear from the vacuum. One falls in, the other escapes, stealing a tiny bit of the black hole's mass. Over unimaginable timescales, the black hole evaporates, shrinking and fading until it disappears. The process is slow beyond comprehension. A black hole of stellar mass would take 10 to the power of 67 years to vanish. But it reveals that even at the edge of forever, time still moves, however slowly. In the final moments of evaporation, the black hole becomes smaller and hotter, radiating more intensely until it releases its last burst of energy. What remains afterward is unknown. Some theories suggest that the information once trapped inside is released through subtle correlations in the radiation. Others propose that the information is preserved in a remnant or encoded on the event horizon itself, a concept known as the holographic principle. If true, it would mean that everything falling into a black hole leaves a shadow of information on its surface, a record of history written in geometry. Thus, the edge of forever is not pure silence, but transformation. Time does not end abruptly at the horizon. It slows, stretches, and redefines itself. To cross into a black hole is not to fall into emptiness, but to enter a different structure of reality, one that challenges every intuition built within ordinary space-time. From the outside, black holes seem like endings. From the inside, they may be beginnings of something we cannot yet comprehend. When we look at images of black holes, the glowing rings captured by the Event Horizon Telescope, we are not seeing matter itself, but the shape of space-time made visible. The darkness at the center marks the region where light cannot escape, the place where time has turned inward. Around it, the swirling ring of light reveals photons orbiting near the brink of forever, caught between escape and capture. Every flicker in that halo is a whisper of time's distortion, a trace of gravity's artistry. To stand before such a phenomenon, even in imagination, is to confront the fragility of our understanding. Time, once thought universal, proves to be malleable, mutable, and ultimately local. Gravity does not merely slow clocks, it defines what clocks mean. The black hole is not an absence but a mirror, showing us the deepest truth of the universe, that the shape of time is the shape of existence itself. And yet, as strange as these regions are, they remain part of the same continuum that shapes Earth's gentle gravity and the slow ticking of our days. The same equations that describe satellites in orbit also describe the event horizon of a black hole. The difference is only in degree. The same geometry, deepened to infinity. Time does not change its nature, it only reveals it. At the edge of forever, the universe folds back upon itself. Seconds stretch beyond measure, distances collapse into points, and the future becomes inseparable from the present. In those depths, gravity's hand closes around time, not to crush it, but to show what it truly is. A dimension, curved, fluid, and endlessly mysterious. To approach a black hole, then, is to approach truth. The truth that gravity and time are not separate, but one. That the slowing of clocks and the fall of stars are different verses of the same cosmic poem. And in that poem lies a final whisper, that wherever gravity deepens, time stretches thin, not to vanish, but to remind us that the universe itself is still unfolding, still falling, still dreaming through the infinite geometry of space-time. We are used to thinking of space as the stage and time as the rhythm that unfolds upon it. But in the language of relativity, this distinction dissolves. Space and time are not separate arenas. They are coordinates of a single fabric. Space-time. What we call motion through space is simply a different way of moving through time. Every point in the universe, every particle, every beam of light occupies both, interwoven in a geometry that defines not only where things are, but when they are. It is difficult to feel this unity because we live at human speeds, within gentle gravity, where the curvature of space-time is subtle and forgiving. To our senses, time feels distinct from space, flowing forward as we stand still. But beneath that illusion, every step we take and every heartbeat we count traces a line through space-time, a world line that bends as Earth moves around the sun, as the sun drifts through the galaxy, as the galaxy itself turns through the expanding universe. Each of us is a thread in that vast tapestry, woven into the cosmic continuum. Einstein's great insight was that the laws of physics look the same to all observers moving freely through this fabric. There is no preferred frame, no absolute motion, no universal clock. The universe does not possess a single heartbeat marking cosmic time. Instead, each observer carries their own clock, their own rhythm, dictated by their velocity and by the curvature of the space-time through which they move. The fusion of space and time means that to move through one is to move differently through the other. The faster you travel through space, the slower you move through time. The stronger the gravity you inhabit, the more time bends relative to distant regions. Mathematically, this union of space and time is captured in the space-time interval, the true distance between events in the four-dimensional continuum. Two events that appear separated by space and by time may, in the deeper geometry, lie along the same path. The quantity that remains invariant, that all observers agree upon, is not spatial distance or duration alone, but the combined measure of both. This invariant is what allows the universe to maintain order even when time and space stretch and contract differently for different observers. To visualize space-time, physicists often speak of light cones, diagrams that show the directions along which information and causality can travel. The cone's tip marks the present moment of an event. Its sides trace the possible paths that light could take. Inside the cone lies the region that can be influenced by or can influence the event, the possible futures and pasts. Outside the cone lie regions forever inaccessible, disconnected by the finite speed of light. In flat space-time, these cones stand upright, symmetrical and unwavering. But in curved space-time, near massive bodies, they tilt. Gravity bends the cones inward, narrowing the future's possibilities. The closer you move toward a massive object, the more those cones lean until near a black hole's event horizon, they tip completely inward. There, every direction through space points toward the same inevitable destination, the center of gravity's well. The very direction of time itself curves toward mass. This image is not mere metaphor, it is geometry made real. The flow of time, the shape of motion, and the limits of causality all arise from how these light cones are arranged. When gravity changes the curvature, it does not simply slow clocks. It changes the direction of what we mean by future. The tilting of time near massive bodies means that what is forward in time for one observer might be downward in space for another. To approach a black hole is to watch the concept of direction dissolve. Once we accept time as a dimension of space, a new clarity emerges. We can no longer speak of the universe evolving in time, because time is part of the universe's structure, not something outside it. The cosmos is not a movie being played frame by frame, but a completed four-dimensional shape, a space-time manifold containing all events that ever were or will be. Our consciousness moves through this manifold, experiencing one slice at a time, giving the illusion of flow. In truth, the past, present, and future coexist as different regions of space-time's vast architecture. This view, sometimes called the block universe, feels strange to human intuition. We feel the arrow of time as a flow, a relentless progression from before to after. But in Einstein's geometry, that flow is not a fundamental feature of reality. It is the consequence of how we, as beings embedded within the structure, experience it. Our brains are patterns of entropy increasing. Our memories accumulate in one direction, giving us the sense that time passes. Yet, in the grand geometry, the moments of our lives already exist as a single continuous line. What changes is not time itself, but our position within it. From this perspective, motion becomes a kind of trade between space and time. When you move faster through space, you consume less of your motion through time. This is why moving objects age more slowly. Their world lines tilt through space-time, favoring spatial displacement over temporal progression. The speed of light marks the ultimate boundary of this exchange. Photons, which move entirely through space, experience no passage of time at all. Their world lines lie entirely on the surface of light cones, skimming the edge of causality. From a photon's perspective, emission and absorption happen in the same instant. There is no interval between them. The universe, for light, has no duration. This connection between motion and time becomes especially striking when viewed cosmically. The expansion of the universe is not an explosion in space, but an expansion of space-time itself. Galaxies are not moving through pre-existing space. They are carried along as space itself stretches. The distances between them increase, not because they are speeding apart, but because the geometry of space-time changes with time's dimension included. The fabric itself is expanding, and with it, the measure of cosmic time. When we speak of the universe's age, about 13.8 billion years, we are referring to proper time measured along a particular set of world lines, those that move with the cosmic expansion, neither falling into galaxies nor escaping into voids. This cosmic time gives us a reference, but it is not universal. In deep gravitational wells, clocks run slower relative to that standard. In intergalactic space, far from mass, time flows faster. The universe has no single rhythm. It breathes with a million different tempos, all set by curvature. Recognizing time as a dimension of space allows us to see gravity's role not as a force, but as architecture. Mass and energy sculpt spacetime's geometry, and that geometry dictates how time flows. The slower ticking of clocks near planets, the redshift of light climbing from stars, the distortion of distant galaxies into gravitational lenses, all are expressions of this one principle. Gravity is the geometry of time made visible. It also means that when we look across the cosmos, we are not just looking through distance, we are looking through time itself. The light from a galaxy a billion light years away shows us how it was a billion years ago, because light's travel path is a diagonal through space-time, crossing both space and time dimensions together. Every image in the sky is a slice of the four-dimensional universe, projected into our three-dimensional perception. When we gaze into the night, we are not seeing the present, but a layered atlas of history. In this geometry, the past and future are not separate regions to be reached, but directions to be followed. Move along one axis, and you travel through space. Move along another, and you travel through time. But these directions are not fixed. Gravity can rotate them, twist them, and blur their boundaries. Near a black hole, the tilt of space-time becomes so extreme that forward in time points inward in space. The future is no longer ahead, but below. To fall is to move forward in time according to the universe's design. Some physicists suspect that this curvature of time is not limited to gravity, but underlies all change in the universe. Even quantum mechanics, with its mysterious probabilities and uncertainties, may be a reflection of how space-time folds at the smallest scales. Time, in that view, is not continuous, but granular, composed of indivisible units defined by geometry and energy. What we perceive as smooth passage may be the statistical emergence of countless quantum moments stitched together. The union of space and time also reshapes how we think about boundaries. In ordinary language, we speak of past and future as separate, but in space-time, they are simply connected regions. A star's death and a planet's birth may lie in different temporal coordinates, yet they are neighbors in the geometry of the whole. Every cause and effect, every chain of motion, every heartbeat and orbit exists as part of one grand structure, a single four-dimensional sculpture shaped by gravity and energy. To move within this structure is to participate in its curvature. Every atom of your body bends space-time slightly. Every thought, every motion, every breath is part of the geometry. The difference between the grand arcs of galaxies and the pulse of a neuron is scale, not principle. Each follows the same law, inscribed in the shape of space-time. When we understand time as a dimension of space, the question of its flow becomes less about passage and more about perspective. Time does not move. We move through it. The universe is timeless as a whole, yet every observer experiences their journey as motion through time. The river does not flow, yet every boat drifts downstream. Gravity determines the river's bends, and we are carried along, each at our own pace. This realization is humbling, but it is also liberating. It means that the past is not gone, and the future is not yet real. They are both woven into the fabric of the universe, accessible in principle through the right geometry. We cannot return to the past because our world line forbids it, but its existence in space-time remains eternal. The moments of your childhood, the birth of stars, the first flicker of light after the Big Bang, all still exist within the grand continuum. The arrow of time we feel is our local perspective within an unchanging whole. The geometry of space-time unites what once seemed separate: motion, causality, existence, and time. Every curvature of gravity is a bending not only of space, but of the direction of time itself. The universe is not expanding into anything. It is unfolding its own geometry. To understand this is to see that we are not observers standing outside of time, but participants within its dimension, threads woven into the cosmic fabric. And as we continue to explore the universe, measuring the flow of distant galaxies and the deep structure of space-time, we begin to sense that this geometry governs not just motion, but evolution itself. The same curvature that bends light and slows clocks also shapes the destiny of the cosmos, its expansion, its structure, its future. Gravity, through the geometry of time, determines not only how the universe moves, but how it becomes. To explore that vast becoming, we must now lift our gaze from the local to the cosmic, from the bending of time near stars to the warping of time across the entire universe. For the same law that curves seconds near Earth also governs the rhythm of galaxies and the expansion of the cosmos itself. Time's dimension, stretched by gravity, does not end at the scale of black holes. It reaches outward, sculpting the age, shape, and destiny of the universe. When we look up at the night sky, we are not seeing the universe as it is, but as it was. Every glimmering star, every galaxy, every faint thread of light is an echo from a different moment in time. The cosmos unfolds before us, not as a flat image, but as a layered chronicle, stretching back billions of years. In that grand panorama, the concept of time takes on new meaning. It is not simply a measure of motion or duration, but a dynamic quantity, shaped and stretched by the universe itself. Gravity, which bends the path of light and slows the ticking of clocks, also sculpts the flow of cosmic history. It is the architect not only of stars and galaxies, but of time's expansion. When Einstein extended his equations to the universe as a whole, he found that space-time could not remain static. It had to expand or contract. The geometry of time and space, bound together in those equations, demanded cosmic motion. The universe itself was dynamic, its very fabric stretching, carrying galaxies like leaves adrift on a boundless sea. In this cosmic ocean, gravity and expansion are in constant conversation. The attraction of matter works to slow the expansion, pulling galaxies toward one another. But the geometry of space-time, infused with energy, drives outward growth. These opposing tendencies, one pulling inward, the other stretching outward, define the rhythm of cosmic time. In regions dense with matter, gravity's hand dominates, slowing time and binding worlds into galaxies and clusters. In the vast spaces between, where the density of matter falls away, expansion takes over, and time flows more freely, faster, almost unrestrained. The concept of cosmic time arises from this balance. It is not the same as the time measured by a clock on Earth or by a pulsar spinning in the depths of space. Cosmic time is a kind of universal reference frame, defined by the expansion of the universe itself. It is measured by observers who move with the cosmic flow, feeling neither the tug of gravity nor the rush of motion, what cosmologists call comoving observers. For them, the universe appears isotropic, the same in all directions, and the ticking of cosmic time is steady, synchronized across the vastness. But even this is an approximation, for gravity introduces subtle variations everywhere. In galaxies, where matter collects into dense wells, time slows relative to the cosmic average. A clock near the heart of a galaxy ticks slightly slower than one drifting in the cosmic void. The effect is small, but real. Over billions of years, the difference accumulates. Regions of deep gravity experience slightly less cosmic aging than empty intergalactic space. The universe, then, is not aging uniformly. Time itself is uneven, stretched and compressed by gravity's influence. At the grandest scales, this unevenness becomes part of the cosmic architecture. The universe's expansion is not uniform either. Gravity slows it locally, while another mysterious influence, dark energy, accelerates it globally. Discovered through the observation of distant supernova, dark energy acts as a kind of negative pressure, driving the expansion faster and faster. Its nature remains unknown, but its effect on time is profound. In a universe dominated by dark energy, the expansion of spacetime accelerates without bound, stretching the intervals between galaxies until they recede beyond each other's light. As this acceleration continues, regions of the cosmos lose causal contact. Light emitted today from a distant galaxy may never reach us because space itself expands faster than the light can cross it. Beyond a certain distance, the cosmic event horizon, communication is impossible. That horizon defines not only the limits of what we can see, but the limits of shared time. Beyond it, other galaxies continue to exist, but their moments no longer overlap with ours. They drift into a future that, for us, will never arrive. This cosmic horizon mirrors the event horizon of a black hole, though on a universal scale. In both cases, geometry defines visibility and causality. The black hole's horizon traps light inward. The cosmic horizon isolates regions outward. Time near either horizon behaves differently. In both, the geometry of space-time dictates what future means for the observer. The deeper truth is that horizons are not barriers but boundaries between timelines, surfaces where the definition of simultaneity changes. When astronomers observe distant supernovae, they see them flicker in slow motion. The explosions unfold more gradually, not because the stars themselves behaved differently, but because their light has traveled across the expanding universe. The stretching of space stretches time itself. A supernova that lasts 1 month in its own galaxy may appear to last longer when viewed from ours, its light dilated by cosmic expansion. This effect, called cosmological time dilation, is not illusion, but the direct result of spacetime's evolution. It tells us that time and distance cannot be separated in an expanding cosmos. They are part of the same fabric. The cosmic microwave background, the faint afterglow of the Big Bang, offers the clearest view of this fabric. It is the oldest light we can see, released when the universe was about 380,000 years old. Before that, the cosmos was a dense plasma of particles and radiation, too hot for light to travel freely. As it cooled and expanded, atoms formed, and photons began their long journey through space and time. That light, stretched by the universe's expansion, has been traveling for nearly 14 billion years, its wavelength elongated from blazing visible light to cold microwaves. The uniformity of this background reveals that, at the largest scales, the universe once shared a common time, a synchronized heartbeat that set the rhythm of cosmic evolution. But even in that early simplicity, seeds of difference were sown. Tiny fluctuations in density, 1 part in 100,000, became the scaffolding of galaxies and clusters. As gravity amplified those fluctuations, regions of higher density grew denser, forming stars and planets. time within those regions began to slow relative to the expanding background. In that slowing lies the origin of structure, gravity's ability to reshape not only matter, but the tempo of existence itself. The interplay between gravity and expansion continues today. On small scales, gravity dominates, holding galaxies and clusters together against the cosmic drift. On large scales, dark energy prevails, driving galaxies apart faster than ever. The result is a universe divided by destiny, bound islands of matter surrounded by an ever-expanding ocean of emptiness. In the far future, each galaxy or cluster will become an isolated realm, its local time disconnected from all others. Cosmic time will fragment into countless separate streams, each flowing alone into the darkness. And yet, even as the expansion accelerates, the geometry remains precise. Einstein's equations still govern the balance between energy, curvature, and time. The Friedmann equations, derived from those same principles, describe how the expansion rate changes with density and pressure. They tell us that the fate of the universe, whether it continues expanding forever, slows to a halt, or collapses again, depends on the balance between matter, radiation, and dark energy. Each term represents a different way that energy shapes the curvature of spacetime. At present, observations suggest that dark energy dominates, meaning the universe will expand eternally. Over trillions of years, galaxies beyond our local group will vanish from view, their light redshifted into invisibility. The stars within our galaxy will burn out, leaving behind white dwarfs, neutron stars, and black holes. Even those remnants will eventually cool and evaporate. Time, in this distant future, will still flow, but with fewer and fewer events to mark its passage. The universe will not end abruptly. It will fade into stillness. In that far epoch, when entropy approaches its maximum and structure dissolves, time itself may lose meaning. Without change, without motion, the distinction between past and future blurs. Gravity, which once carved the patterns of time through its curvature, will have finished its work. The cosmic clock, having ticked through eons of creation and decay, will fall silent. But we are far from that horizon. Today, the universe still teems with motion and complexity. Gravity continues to sculpt stars from gas, planets from dust, and life from atoms. Every galaxy, every cluster, every filament of the cosmic web is a frozen trace of gravity's dialogue with expansion. The slowing of time near mass and the stretching of time across voids combine to create a universe rich with variation. No two clocks in the cosmos tick alike. This diversity of time raises a subtle question. What does it mean to speak of the age of the universe if time itself flows differently everywhere? The standard answer, about 13.8 billion years, refers to cosmic time as measured by co-moving observers. But in deeper gravitational wells, less time has passed. If you could compare two ancient civilizations, one living near a supermassive black hole and the other drifting between galaxies, their histories would unfold at different rates. The same universe would tell different stories, depending on where its narrators stood. Thus, cosmic time is not a single thread, but a vast fabric woven from countless strands of local duration. Gravity bends some, expansion stretches others, and together they form the texture of history. The universe's timeline is not linear but curved, an intricate interplay of geometry, energy, and causality. To grasp this is to realize that time itself is an evolving feature of the cosmos. The deeper the gravity, the slower its pulse. The wider the void, the faster its breath. The expansion of space and the flow of time are one and the same phenomenon, two aspects of space-time's living geometry. Every flicker of starlight, every orbit, every distant quasar is part of this great rhythm, the heartbeat of the universe. And as we measure the light from ancient galaxies, stretched across billions of years, we are listening to that heartbeat echoing through time. The warping of time across the cosmos is not merely a side effect of gravity, it is the reason the universe has structure at all. Without the curvature of time, matter would never have clumped, stars would never have burned, and life would never have emerged to witness it. Time's uneven flow is the artist that shaped creation. From the smallest particle to the largest cluster, from the fall of an apple to the drift of galaxies, the same truth holds. Gravity and time are inseparable. The cosmos is not a static arena filled with motion, but a living geometry in which time itself bends, stretches, and evolves. The universe's expansion is the grandest expression of that bending, the slow unfolding of time's own dimension. To understand this is to glimpse something deeper still, that the warping of time across the universe is not just a phenomenon, but a process of becoming. The universe is not only shaped by gravity, it is perpetually being rewritten by it. Every second that passes on Earth, every century that unfolds in a distant galaxy, contributes to the great narrative of curved time. And so, as we gaze into the darkness and trace the faint light from the beginning of everything, we are not merely observing history, we are feeling the geometry of time itself. For in the expanding universe, gravity and time are not adversaries. They are partners in creation, two voices in the same cosmic song, weaving together the rhythm of existence across the infinite fabric of spacetime. Time moves forward, or at least that is how we experience it. The universe seems to unfold in one direction only, from past to future, from order to disorder, from simplicity to complexity and decay. Yet the laws of physics, in their purest form, make no distinction between forward and backward. The equations that govern motion, light, and gravity work the same in either temporal direction. Nothing in mathematics demands that time must flow one way. And yet, it does. The question is why? The answer lies in entropy, the measure of disorder, the count of possible configurations that a system can take. A deck of cards neatly arranged by suit and number represents low entropy. The same cards shuffled at random represent high entropy. Nature tends to move from fewer possibilities to more. This tendency gives rise to the arrow of time, the sense that tomorrow will differ from yesterday because disorder grows. But gravity complicates this picture. Unlike other forces, gravity clumps rather than disperses. It draws matter together, forming stars, planets, and galaxies. In doing so, it seems to create order, not chaos. Yet this apparent order hides deeper entropy. When matter collapses into stars and black holes, the number of microscopic configurations, the hidden degrees of freedom, skyrockets. A single black hole possesses more entropy than all the gas that ever fell into it. Gravity's collapse, paradoxically, is entropy's growth. The early universe, just after the Big Bang, was nearly uniform, smooth, hot, and filled with light. At first glance, such uniformity seems disordered. But in gravitational terms, it was astonishingly low entropy. Smoothness meant that matter had not yet clumped, that gravity's potential to create structure remained untapped. As the universe expanded and cooled, gravity began to amplify tiny fluctuations, pulling matter into filaments, stars, and galaxies. Entropy rose not because the universe became more chaotic, but because gravity's degrees of freedom awakened. Every collapsing star, every forming galaxy, was an increase in the entropy of spacetime itself. This connection between gravity and entropy defines the true arrow of time. The direction in which entropy increases is the direction we call forward. In deep gravitational wells, entropy grows faster, matter heats, radiation escapes, and clocks slow. The very places where time runs slowest are the same places where the arrow of time burns brightest. Gravity and entropy are intertwined, shaping both the geometry of space and the flow of time within it. Black holes represent the ultimate expression of this unity. According to thermodynamics, entropy measures the information hidden from us. For black holes, that information corresponds to everything that has fallen inside. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This fact, discovered by Jacob Bekenstein and confirmed by Stephen Hawking, implies that all the information about what lies within the black hole is encoded on its surface. Each patch of horizon area, equal to 1 Planck length squared, carries 1 unit of information. This principle, that the universe's information content scales with area, hints at a holographic nature of reality, where what we perceive as 3-dimensional may be projected from deeper, 2-dimensional laws. As a black hole absorbs matter, its surface area grows, and so does its entropy. When it emits Hawking radiation, it loses mass, shrinking its horizon and decreasing its entropy, but only temporarily. The total entropy, including the emitted radiation, still increases. The second law of thermodynamics remains unbroken, even at the edge of forever. In this cosmic thermodynamic view, the arrow of time is not simply psychological or emergent, it is gravitational. The universe's structure ensures that entropy will continue to rise as stars burn, galaxies merge, and black holes evaporate. Even the expansion of the universe contributes, as space itself fills with radiation stretched into lower and lower energy, increasing the number of possible configurations. Yet the arrow of time may not always have existed. Near the Big Bang, the universe's low entropy initial state set the stage for everything that followed. Why that initial smoothness occurred remains one of cosmology's greatest mysteries. Some theories propose that it was a quantum fluctuation, a rare ordered state from which disorder could grow. Others suggest that entropy's arrow may reverse beyond certain cosmic horizons or in other universes entirely. In some speculative models, gravity might even create new arrows of time whenever space-time branches, birthing new regions where entropy resets and begins to climb again. Entropy, then, is not just a measure of disorder, but of possibility, of how many ways the universe can rearrange itself while remaining the same in essence. Gravity shapes those possibilities by determining how energy and matter can move. Every star that ignites, every planet that cools, every black hole that grows contributes to the greater counting of entropy, and through it, to the forward march of time. Our own lives are part of this vast thermodynamic flow. The warmth of our bodies, the glow of sunlight, the decay of fuel, and the growth of plants all depend on entropy's ascent. We live in a pocket of temporary order sustained by the imbalance between the hot sun and the cold void of space. Life exists in the gradient between energy sources and sinks, drawing structure from entropy's inevitable rise. Even consciousness, the awareness of time's passage, may be an emergent consequence of this thermodynamic imbalance. One day, however, the gradients will fade. Stars will exhaust their fuel, black holes will evaporate, and all energy will spread evenly across space. In that distant future, entropy will reach its maximum, and time, as we understand it, will lose direction. Without difference, without change, there can be no before or after. The arrow will dissolve into stillness. Yet that fate is not despair, but completion. The arrow of time, born from gravity's deep potential and entropy's endless climb, will have fulfilled its purpose, to transform simplicity into structure, and structure into equilibrium. From the smooth birth of the cosmos to its quiet heat death, the flow of time is the story of entropy written in geometry. Perhaps in some deeper sense, gravity does not merely bend time, but gives it meaning. The curvature of space-time and the growth of entropy are two sides of the same cosmic process. One shapes the other, and together they define the universe's unfolding. Time is the measure of entropy's ascent, and gravity is the sculptor that gives that ascent its form. In that sense, the arrow of time is not just the ticking of clocks or the aging of stars. It is the slow, inevitable deepening of the universe's geometry, the quiet transformation of potential into history, Time, as we understand it, may not be fundamental. It might not be a background stage on which the universe unfolds, but something that emerges from the structure of reality itself, a byproduct of gravity's geometry. The deeper we explore the link between curvature and causality, the more it seems that time is not a thing that exists independently, but something generated by the relationships between energy, matter, and spacetime. Einstein's theory showed that gravity is the curvature of spacetime, not a force pulling at objects. But what if that curvature does more than just shape time? What if it creates it? When spacetime bends, the rate of time's flow changes. In regions of strong gravity, clocks run slower. Near black holes, they nearly stop. At the very center, where curvature becomes infinite, the concept of time breaks entirely. If gravity can destroy time, perhaps it can also bring it into being. In the realm of quantum gravity, where space-time itself becomes uncertain, this question grows sharper. The equations that describe the quantum structure of the universe, such as the Wheeler-DeWitt equation, contain no explicit time variable. They describe a cosmos in perfect stillness, where all possible configurations coexist timelessly. In such models, time is not a given quantity, but an emergent one, arising only when parts of the universe interact and define change relative to one another. Loop quantum gravity, a theory that seeks to quantize spacetime itself, suggests that space and time are composed of discrete units, finite grains of geometry, woven together by spin networks. In this picture, there is no continuous flow of time beneath the Planck scale, only transitions between quantum states. What we perceive as the passage of time is the large-scale effect of countless microscopic changes. Time, then, is not a river, but a sequence of quantum ripples that, when viewed from afar, merge into a smooth current. This perspective reshapes the meaning of gravity. Rather than being a static curvature of a pre-existing spacetime, gravity could be the process through which spacetime, and thus time, comes into existence. The gravitational field, encoded in the geometry of the universe, may itself define what it means for one event to follow another. Without gravity, without curvature, there might be no sequence, no before or after, only an undifferentiated quantum haze. In some approaches to quantum cosmology, such as Carlo Rovelli's relational interpretation, time is not a universal clock, but a measure of change between physical systems. The universe does not evolve in time. Rather, time is the evolution of the universe. Each event defines its own temporal relationship to others, and the sum of those relationships generates what we perceive as flow. Gravity, being the geometry that links all events, is the mechanism through which this relational structure becomes continuous and coherent. There are hints of this connection even in the physics of black holes. The thermodynamic behavior of horizons, their temperature, entropy, and radiation, suggests that spacetime itself possesses microscopic degrees of freedom. The area of a black hole's event horizon corresponds to the number of possible quantum states of spacetime geometry at that boundary. From this view, time's flow near a black hole is not merely slowed. It is being generated by the dynamics of those underlying quantum states. Physicists Ted Jacobson and Thanu Padmanabhan proposed that Einstein's field equations, the cornerstone of general relativity, can be derived from thermodynamic principles. If this is true, then gravity is not a fundamental interaction, but a statistical phenomenon, like temperature or pressure. In that case, time itself may emerge from entropy, as systems of spacetime microstates evolve toward equilibrium. The curvature we interpret as gravity could be the macroscopic shadow of countless microscopic processes, each one a flicker of proto-time. This view leads to a profound inversion. Instead of spacetime creating gravity, gravity creates spacetime. The geometry of the universe is not fixed, but arises from the thermodynamics of its own microscopic constituents. The same principle that governs the flow of heat in a gas may govern the flow of time in the cosmos. When energy moves through spacetime, it disturbs the equilibrium of its underlying quantum fabric, and that disturbance, that imbalance, becomes the arrow of time. If this is true, then the origin of time coincides with the birth of the universe. The Big Bang would not simply mark the beginning of time, it would be the process through which time emerged. Before it, there may have been no temporal dimension at all, no sequence, no causality, no rhythm. Only when gravity condensed matter and energy into structure did the dimension of time unfold, allowing change and evolution to occur. The universe, in this sense, did not start in time. Time started with the universe. This perspective also offers a new way to think about black holes. Inside them, where gravity grows infinitely strong, the structure of time collapses. But in the thermodynamics of the event horizon, where entropy and temperature define order, a new kind of time may emerge, one tied not to external geometry, but to the internal evolution of quantum information. The black hole's horizon might serve as a generator of time, its fluctuations encoding the flow of reality itself. If gravity gives birth to time, then time is not a universal substance, but a local property of curved geometry. Each region of spacetime generates its own clock, its own rhythm of becoming. Near massive stars, time flows sluggishly. Between galaxies, it races freely. The diversity of time's tempo across the cosmos is not an accident. It is the natural outcome of gravity's creative power. The universe is not synchronized but symphonic, every region contributing its own measure to the great composition of spacetime. This idea challenges our deepest intuitions. We are accustomed to thinking of time as something absolute, a background against which events occur. But if gravity creates time, then time has no existence apart from the events themselves. Remove the mass, remove the energy, and spacetime becomes flat and featureless, a void without motion or meaning. Time is not a backdrop. It is the unfolding of relationships between things. Perhaps that is why gravity is so mysterious. Of all the forces, it alone refuses to fit neatly into quantum theory. The others, electromagnetism, the strong and weak nuclear interactions, operate within time, exchanging particles across a fixed stage. Gravity, by contrast, is the stage. It defines what time means. To quantize gravity is therefore to quantize time itself, to uncover the hidden machinery that turns stillness into becoming. In the end, the question, does gravity create time, may be equivalent to asking, why does anything happen at all? For without time, there is no change, no evolution, no universe. Gravity, through its shaping of spacetime and its thermodynamic underpinnings, provides the mechanism by which timeless geometry becomes dynamic history. And so, time may be gravity's shadow, a manifestation of curvature perceived from within. We experience its flow because we are made of the same geometry that generates it. Every heartbeat, every orbit, every aging star is part of gravity's slow translation of geometry into experience. When we speak of time beginning, what we mean may be that gravity began to create. The first bending of space-time, the first gradient of energy, the first imbalance in the fabric of the cosmos. These were not events within time, but the genesis of time itself. The universe did not awaken in a pre-existing dawn. It was the dawn, the first breath of duration rising from the silence of geometry. Gravity does not pull, it shapes. Time does not flow, it bends. What we call the movement of seconds is the slow turning of the universe's geometry, the quiet folding and unfolding of space-time under the weight of energy and matter. Beneath every falling stone, every orbiting moon, every drifting galaxy lies an invisible current, not a force that drives them, but a geometry that guides them. To understand this is to realize that the universe is not something happening in time, but something that is time, shaped and reshaped by gravity's hand. We imagine clocks as measuring the passage of moments, yet they do something subtler. They trace the curvature of space-time itself. Each tick of a clock marks not an external rhythm, but a local unfolding of the universe's geometry. Two clocks in different gravitational fields do not disagree because one malfunctions. They disagree because they inhabit different shapes of time. Time has no universal speed. It is a property of position and curvature, an internal language spoken by the cosmos to itself. In this sense, every mass is a sculptor of reality. A mountain, a planet, a star, all press upon the fabric of space-time, bending the direction of duration. Around every object, the geometry of time tilts slightly inward. Where gravity deepens, time slows. Where space expands, time accelerates. The entire universe is a fluid mosaic of overlapping timelines, each shaped by the energy within it. To move through this landscape is to surf along the currents of existence. Einstein's equations describe this with unrelenting precision, yet behind their symbols lies something profoundly human: the realization that there is no universal now. Each observer, each particle, carries its own slice of the present. The word simultaneous loses meaning when gravity bends time. Events that are now for one observer may be past or future for another. The deeper the curvature, the greater the separation of perspectives. Time is not absolute, it is personal. The universe is woven not from instants but from relationships. This relativity of time does not mean chaos, it means coherence. The geometry of space-time ensures that all clocks, though different, remain consistent with one another. The structure of causality, what can influence what, is preserved by the curvature. Light, always traveling at the same speed locally, defines the boundary between possible and impossible connections. The universe's laws guarantee order even in its fluidity. Each moment, though unique, fits perfectly into the greater whole. When we understand this, the old idea of time as a universal river gives way to something richer. Time is not a single stream flowing uniformly forward, but a vast interconnected delta, a web of branching currents, some slower, some faster, all shaped by gravity's contours. We, living beings on a small planet, orbiting an ordinary star, inhabit just one narrow channel of this flow. To see beyond it is to glimpse how existence itself ripples through the geometry of space-time. Near black holes, where curvature grows extreme, those ripples twist almost into stillness. The edge of a black hole, the event horizon, marks not the boundary of space, but the boundary of shared time. To cross it is to enter a region where all futures converge inward, where time's direction becomes indistinguishable from space's. Yet even there, the flow does not cease. To the falling traveler, time proceeds normally. It is only from the outside that motion seems frozen. The paradox is illusion. Both experiences are true within their respective geometries. The universe allows many truths to coexist, each valid in its own frame. This is the deepest lesson of relativity. Reality has no single perspective. The cosmos is not a stage observed from outside, but a self-observing structure. We are part of the geometry that bends, part of the flow that curves. Every thought, every observation, every equation we write is an echo of space-time reflecting upon itself. The physicist's insight is not external knowledge, but internal recognition. The universe learning to describe its own form. If gravity sculpts the shape of time, then consciousness is the awareness of that sculpture. Our sense of flow, of before and after, arises because we inhabit a geometry in motion. The brain's perception of time is a microcosm of space-time's curvature, a collection of patterns evolving according to physical law. Memory, anticipation, causality, all mirror the structure of the universe that created them. We are time made aware of its own unfolding. The illusion of universal time, the belief that seconds pass equally for all, was born from our limited vantage point. Standing on the surface of Earth, we live within gentle curvature, where differences in gravity and velocity are too small to sense. But our satellites, our telescopes, and our mathematics reveal what intuition cannot, that time is elastic. Without relativistic corrections, our global positioning systems would fail within minutes. The satellite's clocks, high above Earth, tick slightly faster because they ride a shallower curve in spacetime. Every map, every navigation, every signal we send is a testament to the fact that time's flow is sculpted by gravity. The geometry that governs satellites also governs stars, galaxies, and the universe itself. On cosmic scales, gravity slows time within galaxies, while the expansion of space accelerates it across voids. The balance between these effects shapes the rhythm of the cosmos. Galaxies live in slow time. The empty reaches between them race ahead. The deeper the gravitational well, the slower its inhabitants age relative to the vast expanding sea around them. Time, it seems, is not a single melody, but a chord, each note tuned to the curvature that sustains it. And yet, there is unity within this diversity. Einstein's field equations bind all these variations together, ensuring that the curvature of space-time remains continuous. No matter how warped, the geometry never tears. Even black holes, where time seems to end, connect seamlessly to the universe beyond. The flow of existence never truly halts. It merely changes direction. The laws of physics preserve continuity across every horizon, even those we cannot cross. In this light, gravity's role becomes almost poetic. It does not simply attract or confine, it connects. It ties together all points of the universe through the structure of time. When a planet orbits a star, it is not pulled by invisible threads, but follows a path carved into the geometry of duration. When light bends around a galaxy, it is not deflected by force, but guided by the curvature of its own future. The universe moves not because something pushes it, but because its shape allows no other motion. This understanding dissolves the last remnants of mechanical thinking. Gravity is not an actor within time, but the director of time's stage. It decides how clocks tick, how paths curve, how causality unfolds. In its presence, time becomes a variable quantity. Not an independent measure, but an emergent property of geometry. The deeper the gravity, the denser the flow, and so, every moment of existence is a ripple in this vast curvature. When you drop a stone into a pond, waves spread outward in circles. When a star collapses, ripples in space-time, gravitational waves, radiate through the cosmos, carrying information about the event. These waves are not vibrations of air or light, but of space-time itself. They are the universe's voice, speaking in the language of geometry. Detectors on Earth have now heard that voice, faint but unmistakable, the sound of two black holes merging, time itself trembling under their union. Each detection reminds us that we are immersed in this flow. The universe is not static, but alive with movement at every scale. Galaxies collide, stars are born and die, and space-time stretches in response. The same geometry that bends starlight also measures our seconds. Gravity's curvature and time's passage are not separate phenomena. They are one and the same. When we trace this understanding to its limit, we arrive at a simple but profound truth. The universe does not exist in time, it exists as time. Every heartbeat, every orbit, every gravitational ripple is a manifestation of this single, continuous process, the self-curving, self-evolving fabric of reality. Wherever gravity deepens, time stretches thin. Every falling star, every collapsing core, every distant galaxy expanding into darkness is a note in this eternal composition. Gravity flows, not as a force, but as the shape of existence itself. And within that shape, we, brief sparks of awareness, drift, measure, and marvel, carried along by the river that does not flow, yet moves everything it touches.